This next section is really kind of just an extension of the last one, because we know that a lot of real applications exhibit normal distributions. However, they're not going to be standard normal distributions, because that needed something very specific of having a mean of 0 and a standard deviation of 1. So if you think about some of our realistic sets we've talked about that have have normal distributions, heights are like that. IQs, weights of individuals, all of these are normal distributions. But definitely the average is not 0, the average height is not 0 inches, the average IQ is not 0, and our standard deviation isn't 1. But there still is that mean that's in the center, and then the standard deviation gives you that symmetry around it. So when we started way back in the beginning of the semester, we talked about calculating those z-scores, and that told us how many standard deviations we were from the mean. What that does is it allows us to actually transform any data into a standard normal distribution, so then we can still apply all of those z-scores and tables to figure out probabilities. So just to give you a picture as to what's going on, here is our normal distribution. So for the normal distribution, that mean is smack dab in the center, and then you can keep going out one standard deviation to be able to find more information. Likewise, if you subtract one standard deviation and keep doing that, you can go ahead and find these other pieces. But if we want to get standard normal, that's going to have a mean of 0 and a standard deviation of 1. So you're really just going out 1 in each direction instead. The way we can actually transform from one to the other is using that z-score. So to make the middle be 0, what we do is we take that previous value, so these were all x values, and we find the value of z by taking our number we're given, subtracting the mean, and dividing by the standard deviation. And so this will get us to those z-scores and put everything on the same scale. So every single one of our x values can be transformed to z-scores. And then once I know the z-score, I can still apply the same thing. If I need to know the area to the left of here, instead, I'm just going to look at the area to the left of the corresponding z-score, and it will still be the same. So then I can get the probability of having a value less than this number, okay? So pretty much you just have to find the z-score, and then you're going to be able to use the tables. Or vice versa, maybe we need to know the probability and we have to reverse engineer what is this value I'm looking for. So we're going to start with an example. Heights of men are normally distributed with a mean of 68.6 and a standard deviation of 2.8 inches. We want to find the percentage of men who are taller than 72 inches. So again, always draw a picture here, but we're starting with x values, and these are the heights that are given. The mean is 68.6. And what I'm searching for is men who are taller than 72 inches. So that's going to fall somewhere over here. And if I want the men that are taller than 72 inches, I'm really searching for the area under this curve. But what I need to do is I need to put it on that z-scale. So what I like to do is right underneath, I like to find the corresponding z-scores. So I'll call this the z-scale. The 68 is going to transform right into 0. Now I need the z-score corresponding to 72. And so in this case, I'm going to take the value I'm given, I subtract the mean, and then divide it by the standard deviation, which is 2.8. So if I plug this into a calculator, my z-score only has to go out to 2 decimals. It's about 1.21. So what I'm going to do is I'm going to use my z-table, and I'm going to go to 1.21 and that's going to give me the area to the left of the curve. So using our z-table, the area to the left of 1.21 and really hence the area to the left of 72 is the following. So I've got my charts at the end of this PDF again, so I'm going to go ahead and scroll all the way down. I need positive z values, and I need 1.21. So the area to the left, rounding to 4 decimals, is 0.8869. So the area to the left of 72 inches is 0.8869. Okay. So if I want the percentage of men who are taller, the percentage higher than 72 inches is 1 minus this amount, which gives us 0.1131, or 11.31% of men are taller than 72 inches. Okay? So again, it's just a matter of transforming these to the z-scores, and then still everything applies in the same way. So let's try another example, similar but more complicated because it's going to be between values. But until recently, the U.S. Air Force required that pilots have heights between 64 inches and 77 inches. Heights of women were normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. We want to figure out what percent of women met the height requirement. So again, starting out by just drawing my normal distribution. For women, that mean height is 63.7 inches. And we're specifically looking for people between 64, which is pretty close to 63.7, and then 77 inches. So this is my X values, which is that height scale. And I'm looking for what is the area between these two numbers. Okay. But to do that, I need to go ahead and put this on that Z scale. So the 63.7 falls right in the middle. And we'll start by doing the 64 inches. If I want that Z score, I take 64, subtract the mean, and then I divide by the standard deviation, which is 2.9. So if I do this and I go to 2 decimal places, this gives me 0.10. So this value that's important is 0.10. Then I need to do the same thing with the 77 inches. And that corresponding z-score is just 77 minus the same thing over the same thing. So when you plug this in, this is about 4.59, okay? So I need to figure out the area in between. So to do that, I want the area to the left of 77, which gives me all of this. And then I need to remove the area to the left of 64 to get the piece in between. Okay. So using the z-table, the area to the left of z being 0.10 is, well, for that we gotta go to the table. So going down to positive values, 0.10 would be right here. So rounding, that's 0.5398. So the area to the left is 0.5398, which seems reasonable because, again, 63.7 is in the middle. This is pretty close. It's about 50% to the left. Then I also need the area to the left of z equals 4.59, because that's the value for 77. So in this case, if I go look at 4.59, you can see our table really stops at 3.99. So that is the biggest we go, because after this point, it gets so microscopic. So at that point, you can really just assume it's the 0.999, or even if you assumed it was 1 at that point, it's not a problem. It's so close to that. So most individuals are not, or most females are not above 77 inches. They're really below that. So this value is 0.9999. So the area in between is the difference of the two. 0.9999 minus 0.5398, which is 0.4601 when you subtract them, okay? And what that does, it gives you the percentage of women between 64 inches and 77 inches. So 46.01% of women met that height requirement. So only 46% of women fell into that correct range. Okay. So you can see not much has really changed from the last one. It's just an extra effort of having to find the z-score for whatever values you're given. The one thing that is going to be a little bit different is, what if I need to find that upper bound? So before, we just had to find on the chart the corresponding z-score, and we were good. The problem is, because we're doing these transformations, it's not so clear-cut then what our upper bound value might be. So we're going to do one last example where we go through exactly that. When designing equipment, one common criterion is to use a design that accommodates at least 95% of the population, because you want your design to be inclusive and not hurt or hinder a lot of people. So assuming the heights of adults are normally distributed with a mean of 66.2 inches and a standard deviation of 3.8 inches, we want to figure out what is the height of a door that would allow 95% of adults to walk through without hitting their head. Because obviously you're not going to be able to make every single door as huge to fit every single NBA player there is. But as long as we can do 95%, it's a pretty good accomplishment. So what I'm going to start with is drawing a picture to help me out, because this is definitely not standard normal, but it is normal. So we know adults have a mean height of 66.2 inches. And what I want is to figure out what 95% of people will be shorter than, okay? So I need to figure out what is this number so that 95% of my area falls to the left of it. And 95% as a decimal is 0.95. So I need to figure out what is my z-score that corresponds to this particular value. So if here is my z-scale, here is 0, I want to figure out what does this z need to equal. So we need to find the z-score corresponding to 0.95, which because we go out to 4 decimal places, you just tack on 2 zeros at the end. It's definitely going to be to the right, so it's going to be a positive z-score. So I need to go into my positive z table, and I need to look at where I hit 95%. So here's 94%, and if I keep going this way, this looks like the very first time I hit 95%. It's not perfect, but it's pretty close here. So this particular z value would be 1.6, and then looking at this value, it'd be 1.65, okay? You really could also probably do the number in between these because you see 0.495, 0.95, pretty close. But again, you have some tolerance for it. So we can say that our z value is 1.65. So our z is 1.65. Okay. So this right here is 1.65. But what I really want is this number here. Okay. So we need to find x. But what I do know is that my z-score is found by doing x minus the mean over the standard deviation. I have z, I have the mean, and I have my standard deviation, so I can go ahead and I can solve for x utilizing that. So plugging in all of the pieces, my z value is 1.65. X is unknown. My mean is 66.2. And then going back up top, my standard deviation is 3.8. So we're going to divide by 3.8. Now, if I want to solve for x, well, I need to get rid of that division first. So I'm going to go ahead and multiply both sides by 3.8. So times by 3.8 times by 3.8. And that will make these two cancel. And so if I do 3.8 times 1.65, that gives me 6.27 is equal to x minus 66.2. And then to solve for x, we go ahead and add 66.2 to both sides. That makes these two cancel. And if I go ahead and add 66.2, that gives me 72.47 is equal to x. Okay. So really just rounding this, the x value that would accommodate 95% of people is around 72.5 inches. So again, extra work that you have to do, but it still puts it on the same scale and everything we've already learned still applies.